Hi, everyone. We're going to give folks a minute or so to log in before we get started here. All right. Well, thank you, everyone, for joining our webinar entitled SonTek ADCP Training Essentials, Your Questions Answered. I'm Chris Irossi. I'm the marketing manager here at SonTek in San Diego, and we really appreciate you joining us here today. So exactly what can you expect from today's webinar event? Well, first of all, you're going to get to know and engage with our technical experts who you see here on the screen and who are here as a panel. We're also going to dig deeper into questions frequently asked by SonTek ADCP users. Specifically, we're going to address the top 6 most frequently asked questions. And then finally, you're going to be the first to have access to our newly launched video training series. We're really excited about this series, and we're glad we're going to be able to preview it with you today. So before we get officially started, let me introduce you to our panelists. First off, we have Isaac Jones, who's been with the company since 2011. He's held various positions during his tenure. He started out in customer technical support and he eventually moved into application engineering, where he worked extensively in the US and abroad, educating our customers and water monitoring professionals in the use of the award-winning River Surveyor M9 and S5 systems, as well as other innovative SonTek ADCPs and CTD technology. We also have our Brittany Jenner. She joined SonTek in 2012, and over the years, she's taken on different roles and responsibilities from technical support to outside sales. Recently, she joined the product management team as a product specialist. Prior to SonTek, she gained experience collecting data with acoustic instruments in saltwater marsh ecosystems. Brittany earned her bachelor's and master's in geology from the University of Maryland, College Park. And also, we have Dr. Xue Fan, who joined SonTek in 2015 as part of our technical support group, offering on-call field support and training for customers operating ADCP instrumentation around the world. She later assumed the role of application engineer. Now she works as part of our product management team. And as part of her role, Dr. Fan performs field testing on SonTek's newest instrument developments and collaborates with the world's leading hydrologic and oceanographic agencies. So let's go ahead and get started here. So here's our first question, and we're going to have Brittany help us answer this question. And the question is, why choose moving boat versus stationary? Brittany.
All right. Thanks, Chris. So before I actually get into answering this question, I'm going to first start off by defining a discharge measurement and what flow really is. So discharge is the volume of water moving down a river per unit of time. So if you look out at this cross section where we have the RS5 sitting on the hydro board, it's strung up to a tagline, and discharge is the amount of water moving past that tagline per unit of time. Usually that's per second, but it can be any unit of time, per minute, per hour. And so typical units for discharge are cubic feet per second or cubic meters per second. Discharge is commonly referred to as flow or Q, and we're going to use those three interchangeably throughout this webinar. And discharge is the cross-sectional area times the mean channel velocity. And so this equation, Q equals V times A, that's going to pop up a lot throughout the webinar. And the hope is that as we answer each of your questions, we'll tie into what component of discharge we're really speaking to at that time. So now that we have an understanding of what discharge is, let's talk about how to actually compute discharge. So to do this, we need to measure the velocity and the depth And then we'll also measure the width for an area, and then we'll be able to calculate discharge from those three variables. We can do this if we take a cross section and we divide it up into many different subsections, as we see in that center cross section there. We can calculate that discharge in a panel and then do that in all of the subsections across that cross section, add it all up, and then we have a total Q for that cross section, or a discharge. This is illustrated in the image on the bottom, where you can't even see those subsections because we're collecting data every 1 second. So each profile is even hard to distinguish. And that's a moving boat example, which I'll kind of dive in here. So I've talked about what a discharge measurement is. So now I'm going to define what a moving boat measurement is versus a stationary measurement. So a moving boat measurement sounds like the name. You are moving the boat along a transect. And so you'll start out at an edge. The boat will move across the transect, and as it's moving, it's collecting velocity, depth, and it's tracking its distance for the width. So those are those three components you need to calculate discharge. So after one transect, you'll have one Q value, and then you'll repeat this process in reciprocal pairs, actually, and then you'll take the average of those transects, and that will be your total Q for that measurement. So that's a very simple way of explaining what a moving boat measurement is. Now, the stationary measurement sounds, again, just like its name, stationary. You hold the system in a stationary spot. And this is based on the midsection method or the mean section method. This image I'm showing here is actually from our flow tracker manual. That's our weighting solution. And we actually employ the same midsection method and mean section in the flow tracker as we do in our ADCP software. But instead of collecting a point measurement, we're collecting an entire velocity profile. So what that looks like with an ADCP, you're holding it stationary in one spot. You're collecting your depth, your velocity data. You're marking where on your tagline you are, so that gives you your width, or you're using GNSS for your station spacing. And then once you repeat that process at each of these stations along your transect, you'll add up all those individual Qs, and then you'll have your total Q for that transect. So those are the two options for measuring discharge with an ADCP. Now I'll finally answer the question. Which one do you choose over the other? And there are a lot of different factors that come into play when making this decision. So I've got a decision tree, very simple decision tree on the left-hand side, and then I have all the factors that come into play on the right-hand side. So you'll need to think about your site and what conditions you'll be having to deal with. Will you have a moving bed or any magnetic interference? And then you need to think about what kind of velocity factors will come into play. Do you have any turbulence or eddies? And then really important is your resources. So how many people are actually going to be able to go out and make that measurement? And then what kind of equipment do you have? Do you have access to a GNSS system, or do you only have bottom tracking available? These things are good to know. And then also, actually, what is the range of your instrument? If you have an RS5 versus an M9, those have different profiling ranges and different depth ranges. So understanding your equipment is also important for making the decision on what type of measurement to use. And then, of course, your infrastructure. Do you have a bridge, a cableway? Do you have a remote boat or a crewed boat? Those are all going to impact your decision here. So when I look at the decision tree, I usually start with, can I make a moving boat measurement? The moving boat measurement is going to gather a lot more data compared to the stationary, because you're gathering a velocity profile every 1 second. So you're covering the entire cross section. So if I can make a moving boat measurement, that's going to be my first choice. So in order to do that, I'm going to need to walk down the decision tree, and I have to be able to check a box and say yes on every vertical sort of line here. So if I want to do a moving boat measurement and I have good bottom track data, then I'm good to go and I can continue on. Or if I have a good GNSS track and I don't have any magnetic or compass interference, then I can also use the moving boat method. But if I did have magnetic interference, then a GNSS track would not be a good option. And at that point, I could use the stationary method if I'd like. So the stationary method is a great option when you have a moving bed present, and we'll talk more about what a moving bed is later on. But if you do test for one and you know that it's present, then stationary is a good option if you do not have GPS or if you have magnetic interference. And then another reason why you might want to choose the stationary method over the moving boat is if you're encountering challenging conditions during your measurement. So during flooding, you might have high sediment load, and that's going to make tracking where the ADCP is a little bit difficult in a moving boat situation. And so sometimes by holding the system stationary in one place and allowing it to average and you'll have a better chance of getting your velocity and depth data so that you can actually make that discharge computation. So the video series that we'll be launching right after this webinar is going to cover in detail how to make a moving boat measurement. So we have separate chapters on preparing your measurement, testing for a moving bed, reviewing data. And so we decided to add in a bonus chapter on how to do a stationary measurement. So if you're interested in this, I encourage you to check out chapter 8. I walk through step-by-step instructions on how to make a midsection measurement in the RSQ software. The other thing I do want to note is that RSQ software has both moving boat and stationary built into the one software. So you have both of those available with the RS5. With the M9 and S5, you will need to launch up 2 separate programs, Reverse Surveyor Live for your moving boat and Reverse Surveyor Stationary Live for your stationary measurement.
All right, well, thank you for that, Brittany. Isaac, we'll go ahead, have you answer this next question, which is, why is an accurate transducer depth critical?
Thank you, Chris. So we'll go ahead and dive into it. And I'll start off with defining what a transducer depth is, just for those who don't know or might not know specifically what the transducer depth is. And so what the transducer depth is the distance from the water line on the boat to the center transducer on the ADCP. And so many think that, and not to be confused with just the distance from that the ADCP is protruding below the bottom of the board. It's actually the whole distance from the water line on the boat to the center transducer is the transducer depth. So why is it critical? This is a measured and user entered parameter. Why is it critical? And it's critical because it's factored into the total discharge. So the total discharge, we're going to keep coming back to that. The Q equals velocity times area is made up of different parts that are actually measured. And Brittany will dive into even a better description of what's measured, what's not measured. But part of this total discharge is it's the measured Q, the edge Q, and then the top Q is it factors in this transducer depth, and then there's the bottom Q also. So the top Q is the area of this top area that's now highlighted in yellow, where we don't measure that velocity because it's too close to the system, and then times the velocity in this top area. And the area of the top is the width, which is kind of intuitive. It's just the width of that section. And then the depth of the top, which is maybe not so clear. So the depth of this top section that isn't measured equals the transducer depth plus the blanking distance. And so if you don't have a correct transducer depth, your top area and your top discharge estimate is going to be off. So it affects your total area if you don't have a correct transducer depth. So that's why it's critical. And then, so how much does this really matter? At the beginning of chapter 3 in this video series we're about to launch, I emphasize that it's important, and I show how to measure the transducer depth. But how much does it really matter? And the answer is it really depends. So we'll take a look at a couple of examples. So this is an example of a very small channel, very slow flow with a shallow transducer depth. So the transducer depth is 0.04 meters, and the total area of the measured with the correct transducer depth that was measured at 0.04 meters is 2.63 meters squared, and then the total Q is 0.4 cubic meters per second. If I take that same data file from that measurement in the field and I go in and zero out the transducer depth, we can see that the area decreases and the total Q also decreases. The total Q decreases to 0.37 cubic meters per second. So we have a total Q change of 0.03 cubic meters per second. Sounds like, well, that's not that much, but for this low flow site, that's more than 7.5% different than, or it is 7.5% different from if with the correct transducer depth. So now we'll take a look at a bigger site. And so this is actually from the measurement that we made for the video at the Blue River in Colorado. And here, as you'll see in the video, and you can kind of tell from this screen capture, it was high flow and there's a lot of surface texture. So the transducer depth, we pushed the RS5 all the way down in the board, and the transducer depth was 0.075 meters. And the total area is close to 20 square meters, and the total Q was 38.82 cubic meters per second. So that's with the transducer depth measured and entered in the field. If I take that same data file and then zero out the transducer depth, we see that the area decreases as expected, and the total Q decreases also. So the area changes by 1.66 meters squared, and then the total Q changes by 3.83 cubic meters per second. So almost 10% different with incorrect transducer depth. So this is an extreme example, actual transducer depth to zero, but there's also a large effect if you just don't have the correct transducer, or a varying effect if you don't have the correct transducer depth entered. So that's the why it's important to accurately measure and input your transducer depth. And here's a resource if you want to know more or need a refresher. We have this technical paper online. So here's the URL to that paper, and this QR code will take you to this technical paper, Understanding the Importance of Transducer Depth.
Hey, Isaac, if you do actually enter that incorrectly, are you able to correct it afterwards?
Yes, you can. So that's, as I showed in the examples, that was all done in post-processing. So in the field, we entered the correct transducer depth as we're making the measurements. It's a good question. And went in, and I can zero it out and then apply to that transect or apply to multiple transects to see that effect. Likewise, if you had accidentally left it at zero or measured it incorrectly, you can go back in post-processing and enter the correct transducer depth and then apply to the specific transect or to all transects.
All right, thanks, Isaac. Why don't we go ahead and have you answer the next question as well, which is, why and when would you do a compass calibration?
Thank you, Chris. So we'll get right into it. Okay, so so in the video, in chapter 3, we cover that like kind of how-to of the compass calibration, and we show the software, and we show the compass calibration dance, the compass dance as we call it here at SonTek. But when and why do compass calibration? So the when is before each measurement, you should do a compass calibration. And always, if referencing GNSS or GPS track, you need a good compass calibration. Always, if you're doing a loop method, the loop method's a moving bed detection analysis. And then when moving to a different site to site, you always want to do a compass calibration. And after changing the float or boat ADCP setup or configuration. So if you add or remove antennas, GPS antennas, GNSS hardware, or if you change the transducer depth. And for the RS5, also, if you change the battery, you want to do another compass calibration. So this is, again, covered in the how-to, or the how-to is covered in chapter 3 of the video series, if you want more detail or more on the how. So why do we do a compass calibration? The compass calibration, it calibrates for the local magnetic field. So magnetic fields change from site to site, and then there's local things that can affect it. The compass calibration accounts for that. It also calibrates for your equipment setup. So where you're very local, like right around the ADCP magnetic field. So where the batteries are, what other metal and things are around the ADCP. And then it's needed for transects referencing GNSS or GPS, same thing, but different terminology, to align the ADCP's coordinate system to the satellite position that's received from the GPS. Also, it's needed for accurate magnetic error alerts, which I'll show, and then it's needed for loop moving bed tests as well. So I'll show you an example. So this is an example that was collected here in San Diego along this channel in Mission Bay. You can see in the top right. And this was an example of a good compass calibration. But then the ADCP was, the measurement was taken with a boat along the side of this bridge. And you can see what's plotted here is the magnetic error, is the red curve. And then the dotted line is our threshold of 3.5%. If you exceed that threshold of 3.5%, the magnetic field is much different from the calibrated magnetic field, and the compass is not usable. So this is a good compass calibration, but you can't, there's significant magnetic interference and you can't use the compass at this site. So you need to move farther away from the bridge, or maybe just make the measurement using bottom track. So this next example is an example of a very difficult site, but I'm showing it for two different reasons. So this is the site. There's it's a concrete rectangular channel, and this could be an example. So again, I'm showing the magnetic error is the red curve, and the X's indicate that it's exceeded the our threshold for almost the whole cross section. And at this site, because there's so much, there's a train trestle right downstream, upstream, and then there's like concrete walls and lots of metal here. So this could be an example for this site where the compass was calibrated, but it just, there's not going to be a good compass calibration for this site. Or this could also be if what it looks like, your data would look like if you hadn't done a compass calibration at all, and you're at a clean site and you're making a measurement, and you could just get magnetic error alerts all the way across if you haven't done a compass calibration. So this is kind of an example of what, like, yeah, a bad site for the compass, it's not usable, or if you just not calibrated the compass. So once we've calibrated the compass, you also want to make sure to enter the magnetic declination. And I'll start off by defining the magnetic declination. It's sometimes called magnetic variation. It's the angle between geographic north and magnetic north. And that's illustrated here on the right-hand side. So NG is the direction of geographic north, and then NM is the direction of magnetic north. And that plus delta is the magnetic declination. This is needed to rectify what the magnetic compass in the ADCP is reading to geographic north, and it varies from place to place. And I'll give you a tool for looking that up here at the end of this section. But just what does that look like in the field here on the far left? This is from the Blue River site that we measured during the video series. The magnetic declination we looked up and entered was 8.3 degrees. So we see a Google Earth image. This is from an export from RSQ, a KML file plotted or shown in Google Earth. This is with the correct magnetic declination. You can see the direction of the channel, and the flow vectors, the white flow vectors, line up with the channel and what we expect to see with the flow heading down the channel. The second panel and the yellow stick plot of the vectors shows with no magnetic declination entered. So you can see the velocity vectors are slightly off to the side. That last panel shows both plotted together, which is kind of hard to see, but I'll blow that up. And now you can see that there's an angle between the yellow and white vectors, and that's that 8.3 degree rotation for the entering the magnetic declination. So how do you get the magnetic declination? And there's a good tool out there. There's quite a few good tools out there, but our go-to is the NOAA website, and there's a magnetic declination calculator. So you can follow this URL and enter your latitude and longitude, and it will get the magnetic declination for the place you are in the world. Or if you're on a smartphone and allow the use of your location, then it'll just give you the magnetic declination. So yeah, so to sum it up, use your magnetic declination or enter your magnetic declination and calibrate your compass.
So Isaac, in the video series, you and Brittany performed that compass calibration on the bank. Now, is that the same method that you would use for, say, like a remote controlled boat, or are there other methods that people use?
Yeah, so if it's a small enough remote boat, then I guess you could do that. But most remote boats, you're not going to be doing the compass dance with. So that's a good question. But if the boat's too big or you need to be out in the channel a little bit, you ideally want to be running the motors. You could put the boat in the water and do figure eights out in the water and try and run at the RPMs that you're going to be running as you go across the cross section. Thank you, Xue.
All right. Thank you, Isaac. So for our next question, the question is going to be directed to Xue. And the question is, why choose one track reference over another? So Xue, could you help us answer that question, please?
Yes, as soon as I get my slides here. All right. So let me talk about, first of all, having a track reference and why that's essential during your moving boat measurement. So first of all, what is a track reference? The track reference basically refers to how the ADCP is moving across the channel. So if you look at that photo on the right, the figure on the right, you'll see the boat moving across the channel. So that has the ADCP on it. It's going to be moving in the direction from one bank to another. And then you have the actual flow, those velocity vectors that are moving downstream as you're taking that measurement. So in a different direction compared to that boat movement. So coming back to our first principles, Q is, again, velocity times that area. And that track reference impacts directly that measured water velocity. So when we have an ADCP and you turn it on, it's going to start pinging and recording a total velocity. So it's going to include its own movement plus whatever the water is doing. So when we calculate flow, or Q, we actually want that water velocity alone. So in order to calculate that water velocity, we basically have to use the ADCP total measured velocity minus that ship track velocity. So that ship track velocity is what we refer to as the track reference. All right, so ship tracks or track references, what are the options available to you? All SonTek ADCPs for moving boat measurements will come with bottom track enabled by default. So bottom tracking is when we basically ping off the bottom and calculate how that ADCP is moving with respect to the bottom. And then the other option you'll have is GPS or GNSS. And there are two kind of flavors of GPS or GNSS track references. We call them GGA and VTG, and I'll go into detail in a little bit on these. But for reference, on the bottom there, you see that ship track plot, which you'll see in the moving boat software. And with that, you'll see all the track references plotted on top of each other. So that blue line you'll see is represents bottom track, and you'll see the vectors moving downstream, going up towards the top part of the screen. And then behind that, you'll have the purple and the yellow lines, which represent that GGA and the VTG strings from the GPS or GNSS information. All right, so let's talk in detail about bottom track first. So again, I mentioned that bottom track is basically we're pinging off the bottom and we're looking at that return and calculating how the ADCP is moving with respect to the bottom. So this is a very highly accurate method of tracking your velocities. And it actually calculates the bottom velocity very similarly to the water velocity, so that accuracy of the measurement is the same. Along with that bottom track reference, you'll also measure the water depth, so you kind of get a 2-in-1 measurement with those pings. And then finally, you actually don't need a valid compass heading to get an accurate discharge using bottom track only. Now, Isaac did mention that if you're doing a loop moving bed test, you do need that calibrated compass. This doesn't apply to GPS, which I'll go into in a little bit. If you're looking at your velocity vectors, if you do not have a valid compass calibration, they might look slightly off compared to what reality looks like. But at the end of the day, your discharge value will be accurate, even if you don't have a valid compass heading. So if you're at those sites where either you can't get a good compass calibration or you have that magnetic interference that is messing up your magnetic compass, then bottom track is often a good way to go. Some of the drawbacks of bottom track, number one is moving bed. And so what moving bed refers to is when the flow is either strong enough or the substrate on the bottom is sort of loose enough that basically it moves along with the flow. So the bed is actually moving along with the flow. So if you imagine an ADCP that is sitting still with the bed moving and your bottom tracking, the ADCP is going to think that it's actually moving upstream. So in that way, you get an artificial upstream motion, which ends up biasing your final discharge low. So there are various ways to measure and then correct for a moving bed, even when you are using bottom tracking. So check out chapter 5, which is testing for a moving bed, and Brittany and Isaac go into detail on how you do that. And then finally, bottom track is susceptible to errors when you're in very difficult conditions. So those sorts of things would include vegetation, very high sediment, and a highly variable bottom. And so, for example, that would be, big cobbles and then small stones all in one transect, that sort of thing. All right, let's move on to GPS or GNSS ship tracks. I mentioned that there are two different types, GGA and VTG. So let's talk about GGA first. Some of the features, GGA basically uses the latitude and longitude locations for ship track. And so it builds your ship track across the channel. It's a great way to use your track reference. GGA is susceptible to what we call multipathing. So multipathing occurs when, for example, on this lower left-hand side, you have an image of a site which is surrounded by high canyon walls. And so what happens in multipathing is that signal from the satellite, which reaches your receiver, some signals will reach directly to the receiver and some will end up bouncing off of objects. And that bouncing off of objects is what creates those errors. So this not only applies to canyon walls, but tree cover, especially along the banks, or even high buildings, things like that. So if you have sites which have those tall objects, then you are susceptible to GGA. And what that looks like in the data is pictured to the right here. So you see that purple line, which is the GGA track, and you see those large spikes. So first of all, when you see that in the field, you want to just make sure that that didn't actually occur in reality. If that did, then you probably have bigger problems in terms of your boat operation. But GGA multipathing, this is basically what it looks like. And you want to be cognizant of this sort of artifact. Let's move on to VTG. So VTG uses velocity. So think V velocity. It's very similar calculation to the acoustic Doppler velocity calculations that we use in our acoustic instruments. It's also a great way to calculate your ship track. However, it does require a minimum speed of 0.24 meters per second or 0.8 feet per second. So if you think about how you make a moving boat measurement, you are required to sit at an edge for 10 or more seconds and then move along your transect smoothly and then sit again at another edge. So you want to just make sure to look at your data and look for spikes or artifacts, especially at those edge locations where you aren't moving very quickly. And then you want to try to maintain a speed that's higher than that minimum speed when you're moving along the transect. And then for both GGA and VTG, some of the features, basically you can use these GPS ship tracks when you cannot use bottom track. So that's when you have a moving bed or any other issues with bottom tracking. And then the GPS track references actually provide a redundant ship track for troubleshooting. And I'll go into an example of that next. Some of the requirements for GPS, again, we mentioned this already, but they require a valid compass heading. And so that includes a calibrated magnetic compass, or if you have access to a GPS compass, you can use that as well. And then, as Isaac mentioned before, it does require a proper magnetic declination if you are using that magnetic compass. Okay, so let's talk quickly about how to use those ship track plots for quality control. So you've taken your measurement and you're in the field or in post-processing in your office, and you're looking at that ship track plot that I have plotted here. And the first thing you'll notice is that that blue line, that bottom track line, is substantially shorter than the GPS lines, the purple and the yellow lines. All right, so when you have redundant ship tracks, when you have GPS on top of the bottom track, you can use this as a quality control because you can tell visually, okay, my lines look very different from each other. Remember that the SonTek ADCPs will record all of your ship track data independently throughout the measurement automatically. So if you do have a GPS, you don't have to do anything special, just plug it in and it will record that GPS track for you, even if you do pick bottom track as your primary reference. And then after the fact, you can change that track reference in post-processing. So going back to this measurement, your eye is telling you visually something is very different about these track references, and you need to decide which track reference to pick for your measurement and your final Q or discharge calculation. So in order to do that, you need to figure out why are these ship tracks different. All right, so let's look at the measurement as a whole. If you do look at that left middle panel, that's the QC warnings panel, and you look at some of the samples where they have warnings, you'll notice that they say invalid bottom track. And then towards the bottom of that box, you'll see 9 consecutive samples with invalid bottom track. So when you have 9 or more consecutive samples of invalid bottom track, basically your boat speed is set to 0 and you have no bottom track information to work off of. So not only do you have a shorter width or extent of your ship track because we have no speed information, but that water velocity calculation that you're trying to correct for is likely incorrect because you don't have that bottom track information to correct it. So in this case in particular, it's not because of anything except for the fact that we're getting a lot of invalid bottom tracks based on the conditions at the bottom. And in this specific situation, you would either choose GGA or VTG as your ship track to calculate an accurate Q. And check out Chapter 7 in Office Data Review on how to change your track references after the fact in post-processing. All right, so that was a lot of information. Let me just summarize very quickly. In terms of track references, we have your bottom track, which is, again, always included in all SonTek ADCPs. And then you have your GPS or GNSS options, which include GGA and VTG by default. But this option is optional, so you can either choose or to use it or not. But when you do choose to use GPS, this provides you with a redundant ship track. And what that allows you to do is basically it ensures the usability of your measurement. So when you're in the field, you've taken your measurement, you come back to the office and you realize that your bottom track has issues. If you did have that GPS ship track, then you're able to save that measurement and use your GPS. Otherwise, you might have to go back into the field and retake that measurement. And then, as I mentioned before, those different ship tracks are great visual quality control parameter. So you can look very quickly and see if there are any issues and decide on the fly what you should do and how to deal with those issues. And then if you're interested, chapter 3 of the video series, Preparing for Your Measurement, Isaac and Brittany go over kind of the logic on what they decided in the field on how to choose which track reference to use during that measurement. So just as a reminder, if you do use bottom track, make sure to watch out for moving bed. If you do have moving bed, use GPS or use those corrections from the loop and then SMBA test. If you're using GPS or GNSS ship track, make sure to have a valid compass calibration. If you're using GGA for that ship track, watch out for multipathing. If you're using VTG for that ship track, watch out for moving slower than that minimum speed that I mentioned. So Isaac and Brittany, when you were out in the field, did you have any bottom track issues, or how did you decide which track reference to use?
We didn't have bottom track issues per se, but we did have a few missing bottom track samples, and so we decided to reference the GGA string, the GGA track.
All right, thank you for that, Xue. Why don't we go ahead and have you answer this next question as well, which is why use VB versus BT depth?
All right, so let's talk about depth and measuring depth during a moving boat measurement. So again, going back to Q is velocity times that area. So the depth comes into play in that area parameter. So as Brittany mentioned, we need to calculate that cross-sectional area to get a proper Q. And that cross-sectional area is comprised of the measured area, so that's where that whole transect is covering, plus those edges. So that measured area is determined by basically the depth multiplied by the width for every little section that pieces along the transect. And so with that depth, that's what we're looking for. That's what our ADCPs will calculate for you. The depth references that are available in our ADCPs include a vertical beam depth and a bottom track depth. So let's talk about one versus another, vertical beam versus bottom track depth. So first of all, vertical beam depth. This refers to a depth ping that comes from that central transducer that is basically in the middle and points directly under you or under the ADCP. It's a great way to track your depth. However, it is susceptible to jumps in depth, especially when that bottom is highly variable. So that, again, is sort of large boulders to small boulders, vegetation, that sort of thing. So just keep an eye out for that when you're taking your measurement. And the alternative then is your bottom track depth. So the bottom track depth is actually calculated as an average of those 4 skew beams that are used to ping. And so because it is an average, it is often smoother compared to that vertical beam depth, which is just off of one transducer. So the bottom track depth, while it is an average and it is smoother, it is still susceptible to those highly variable or difficult conditions that the vertical beam also experiences. So just keep that in mind when you're looking at those depth measurements. And something else that the bottom track depth is susceptible to is errors when you're near a vertical or a steep bank. So let me show you what that looks like. All right, so this is an example from a site that is basically a perfectly rectangular cross-section. It's a concrete lined channel here. And so if you imagine this ADCP moving closer and closer to the wall or the bank, if you have a very steep or vertical bank like we have here, if you're using that vertical beam, which is shown in that blue beam on the left top there, you're going to be tracking that depth on the bottom pretty well, all the way very close to that wall. However, if you're using that bottom track depth, which is represented in those red beams, there is going to be a point where one or more beams are going to start hitting that wall before the other beams. So if you do take an average of all the 4 beams, you're going to start seeing a kind of creep up in your depth as you get closer and closer to the wall. So what that looks like is below here, that red line, you see that sloped red line going shallower and shallower. That's that bottom track depth as you're getting closer to the wall. And then if you look at that black line, the vertical beam depth, that basically stays steady until you hit the wall. So generally, if you're using your bottom track depth in a situation like this, and you're calculating the area, you're basically going to be missing that whole area under that triangle, that that you can see in the red line. So just make sure that when you're taking a measurement, you're looking at your bottom track depths and your vertical beam depths and deciding what is actually closest to reality. And just like the track references, these depth references, the vertical beam versus bottom track, is a great tool to use visually in terms of quality control, because you can look at this and say, okay, my bottom track depths and vertical beam depths are very different. So I need to decide which one to use based on which one I think is more correct. All right, so let's talk about switching between vertical beam and bottom track depths. So go back to that slide here. So the M9 and the RS5 will automatically calculate the vertical beam and the bottom track depths for you. So there's no extra setting that you have to set. So there's no extra setting that you have to set. You're going to get both parameters automatically when you take your measurement. And then it will actually automatically fill in with the other depth reference when that chosen one has gaps. So the example is to the right here of that black line is that vertical beam depth again, and you'll see that hole where that the yellow highlight is. And you see that QC warning for that sample says the bottom track is used as a depth reference. So that's the software telling you that my vertical beam had a gap and I'm using the bottom track to fill in. Something to note for those QRev users is that QRev actually defaults to bottom track depth. And so all SonTek ADCPs do come with a vertical beam, but not all ADCPs out there come with a vertical beam. So that's partially the reason why QRev defaults to bottom track depth. So if you are in situations like I mentioned earlier, you just want to be aware of this fact and make sure that you choose the right depth reference given your site situation. You can check out Chapter 7, which is the in-office data review on how to switch between bottom track and vertical beam depths. And there's a quick tip that I wanted to share with you in your post-processing or in the field. You can tell very quickly what reference you're using through the discharge summary. So that's your Control S shortcut. And you'll see those little icons that I've highlighted here. You see BT, so that means that you're actually using your bottom track reference. And then to the right, you see this little blue circle in the middle. That's your vertical beam depth that is used. And then if you change that reference, if you change the reference to, for example, GGA as your track reference and bottom track depth as your depth reference to the right, you'll see those icons change. So that's just a quick way to tell. And I want to go back to a final slide here. Here's just an example that's specific to the M9. So the M9 vertical beam is actually a lower frequency compared to the bottom track beams. So in acoustics, when you have a lower frequency, generally you can actually ping further in the water. And so what that means is the vertical beam is actually able to track deeper compared to those bottom track beams. So the vertical beam range is actually about 80 meters, whereas the bottom track range is about 40 meters. So on the left here, this is an example of a transect done across the Amazon River. And on the top plot there, you'll see that green line that cuts out abruptly, basically once those depths hit almost about 50 meters. So we say 40 meters nominal, but depending on site conditions, it might go a little bit further. And then you'll see that the vertical beam is able to establish the depth beyond that just fine. And so when you're in situations like this, you want to just make sure that you're choosing the right depth reference. So in this case, vertical beam depth, in order to get the correct shape of the channel and then calculate the correct area, which then goes into that Q calculation at the end of the day. All right, so that's vertical beam and bottom track depth in a nutshell.
All right, thank you, Xue. This last question we're going to have Brittany help us answer. And the question is QRev required for post-processing? Brittany.
All right, so we've actually been getting this question a lot more recently as QRev has been adopted around the world. And the short answer is no, it's not required because RSQ and RSL software both have post-processing built in. So you can collect data with your RS5 in RSQ and post-process in RSQ. But the answer is a little bit more complicated than that because many users have to report their data out. And so I want to just start off by just sharing with you what QRev is, because we realize that this is a common question, but not everyone is aware of it. So QRev is a processing software. It was developed by the USGS so that they could compute discharge from moving boat ADCPs. And the real goal was to standardize the computations because they use ADCPs from different manufacturers. And of course, every manufacturer has their own proprietary software. So those computations are just slightly different from manufacturer to manufacturer. So this was a great way for them to standardize and make sure that all of their measurements that they were bringing into their system were all being calculated in the same way. Prior to the development of QRev, the USGS had developed an extrapolation tool. So if you look in the bottom right corner of the screenshot here, you'll see a velocity extrapolation. That's the USGS XTRAP tool. And that XTRAP tool has actually been built directly into RSQ software. And we always try and stay as up to date as possible with the latest version of XTRAP. You can always reach out to us and let us know what version is implemented in our software. So that is one similarity between the two softwares. And so what I'll do now is kind of walk through what those similarities and differences are so that you are aware. So what QRev is going to do, it's going to kind of systematically step through all of your measured data, and then it will extrapolate out your unmeasured areas, so the top, the bottom, and your edges. So I'm going to start with that measured section. So there's a very specific order of operations. QRev is going to filter and interpolate so that every sample has a boat velocity, and that way we can calculate the transect length from the boat velocity, so that's our width. Then QRev will ensure that every sample has a depth value, and then it will ensure that every sample has a water velocity. So we have our transect length, which is our width, and our depth, which gives us our area, and then we have the velocity. So QRev is able to calculate discharge per sample. One really important thing to note is that QRev uses all valid data. That's great, so do we. But the big difference is that QRev will take take invalid data and to interpolate it. That's something that RSQ and River Surveyor Live does not do. We just flag if a sample is invalid to give you the information. All right, so take a deep breath as I walk through this large table with lots of words on it. So on the leftmost column here, those are all the same steps that I just outlined right here: boat velocity, depth, water velocity. I've just put them in table form. So we'll step through each of those operational steps in the processing column. Now, my other columns, I've got an RSQ column, a QRev column, and a QRev filter column. So the first thing you'll notice is that there's no RSQ filter column, and that's because there's no filtering done in RSQ. So that's another difference between the two softwares. So this table is basically illustrating how the different softwares handle invalid samples. So as we go through the order of operations, first we check the boat velocity, and if it has a bottom track reference in RSQ, we're going to flag those as invalid. And then if we have more than 9 consecutive samples of invalid bottom track data, we are going to reset the velocity to 0. In QRev, they will actually linear interpolate this invalid velocity data. Similarly, if you use a GNSS track reference, whenever there's invalid data in RSQ, we're going to flag it as invalid. That sample will not be used, and we'll use the duration of the next valid sample will actually increase. In QRev, they'll do some linear interpolation, again with this track reference. For depths, as Xue mentioned before, QRev handles the depth a little bit differently than RSQ. So in RSQ, we default to the vertical beam as the preferred depth, but of course this is user selectable and you can change it at any time. In QRev, the selection priority is going to be to use the bottom track depths and then a depth sounder, and then vertical beam will be third choice. And when there are invalid depths, QRev is going to do a linear interpolation, whereas in RSQ, we're going to actually hold the last valid depth indefinitely. Now, I do actually want to pause and just say that I'm not mentioning River Surveyor Live right now because you can actually open your M9 and S5 files in RSQ by holding that shift button. So that's why I'm just going over RSQ and QRev right now. So these two software programs, they also handle your side lobe cutoff slightly differently. And that's going to impact our bottom extrapolation, which I'll get in here shortly. So in RSQ, we're going to use just the slant beams for our side lobe cutoff. And in QRev, it's going to use the slant beams and the vertical beam. For our water track, which we're going to use for our velocity, RSQ is not going to do any interpolation if we have an invalid sample, and QRev is going to do an ABBA interpolation. So this is just showing you how the two software programs handle invalid samples so that you understand when you're looking at your data in these two programs. All right, so I've talked through how QRev handles this measured section. Now I'm going to talk about the top layer, the bottom layer, and then I'll close with how it handles the edges. So for this top layer, Isaac actually already touched on this a little bit. We have that region at the top where we're not measuring, and so we need to extrapolate and assign a velocity and an area to that section. So the area is very simple. It's just our transducer depth, which is that distance the transducer is below the water surface, plus our blanking distance, which is controlled by the instrument. So we just need to assign a velocity to that area. For the bottom section, this is not quite as straightforward. We cut off this bottom section due to side lobe interference. So side lobe interference happens because we are sending out an acoustic pulse and it's going to reflect off the bottom at an angle and create interference within our sample volume. And we don't want to include that in our measurement. And so the amount of interference is going to be dependent on the angle of the beams. Here at SonTek, our beams are set at 25 degrees offset. And so we use a very conservative 10% cutoff. So we cut off that bottom 10% of the profile. This is, of course, user controllable, and you can adjust this. QRev follows the manufacturer's cutoff. So if you do not adjust the 10% cutoff in RSQ, then that cutoff will actually match between QRev and RSQ. But it is important to note, if you're looking at other manufacturer data, they may have a different cutoff, and QRev is just going to use the manufacturer's cutoff. And that will then potentially impact what data gets included in your extrapolation. So let's talk about extrapolations. So we need to be able to assign a velocity and an area to the top and bottom layers. So the area we've already talked about with the transducer depth and blanking distance at the top, and then that side lobe cutoff on the bottom. So now we need our velocity. So I mentioned in the beginning of this section that the USGS had come up with this extrapolation tool before they came up with QRev. And this extrapolation tool is great because you can actually load in all of your measured data, and then it will determine what's the best fit given the data from your site. And there's 3 different options for your top fit. There's power, constant, and 3-point. And for the bottom, there's power and no slip. Over here on the right, I'm showing a power extrapolation. And this is the default extrapolation in RSQ. We use a 1/6 power law in RSQ. But once you run the extrapolation program, you can change that. And that's the whole idea behind this program. So you can launch Xtrap from the discharge settings, click on Xtrap method. It will load all of your data from the measurements you have open into the extrapolation tool, and then it will recommend a top and bottom fit as well as an exponent. So if you look in this discharge sensitivity window here, you'll see that in this case, it actually chose a constant for top, no slip on the bottom, and an exponent of 0.3. And then we also give you information on how much this impacts your total Q. So in this case, the constant no slip was actually a 4% difference from that 1/6 power law, which is the default. So 4% is pretty significant. So this tool, again, matches up with the Xtrap tool in RSQ. So this is something that's very similar between the two software programs. So let's actually look at some data in QRev. So this is the extrapolation tool right in QRev. And on the left here, I'm showing a power extrapolation. This is from an RS5. And there's another set of data here on the right. And what I'm going to pose is what type of profile does this look like? These data were collected at the same site, one after another. So one would expect them to look very similar, and they do. They both show a power extrapolation. There's just a bit more variability in the range of velocity on the right side. But you'll notice if you look at the red circle on the right, that QRev in this case actually chose a constant no slip. However, the tech was looking at the data and decided, it really does look like a power, so ended up deciding to select the power fit with a 0.41 exponent. Now, it's good that that user was able to override that. They looked at the data and decided, you know what, this really does look like power. And when we look at the discharge sensitivity here, we can see that in this case, this actually makes a really big difference. So this velocity extrapolation, which is just occurring in that top and bottom, so you might think it's not making a big impact, at some sites can actually make a significant impact. So here, if the tech had gone with constant no slip, that would have been a 7% difference from what they ended up going with, which is the power 0.4 exponent, and 10% difference from the default 1/6 power law. So Xtrap's a great tool for plugging in your data and getting that top and bottom fit. Just make sure to look at your data and make sure that it makes sense to you. All right, so we've gone through the measured data in the center, those top and bottom extrapolations. So we just have the edges left. And QRev uses extrapolations based on Fulford and Sauer, a 1986 paper. And so there are three options when you set up your edge in the software. There's slope, vertical bank, and user estimate. For the sloped, we use a triangular shape coefficient, and RSQ and QRev, they actually use the same exact coefficient here. So if you're looking at data in both of these software, I would expect the edge calculations to be the same. A vertical bank might show some differences, and that's because in RSQ, we're using a range of coefficients, whereas QRev is just using a fixed value for that rectangular shape for a vertical bank. So if you do see some differences in your edge discharge, perhaps it has something to do with the fact that it's a vertical bank and there's a slight difference in the calculation. It's just important to know when there are differences and where you might find them. So I'll wrap up this section here with just going back to that discharge measurement that we made out on the Blue River for our training series. So on the top here, I'm showing RSQ. And I ran the data through RSQ. I did use the extrapolation program, and I ended up with a final discharge of 37.2 cubic meters per second. When I ran those same data through QRev, I got 37.3 cubic meters per second. So in this situation with these data set, there was less than 1% difference. Now, to actually really kind of put a nail on the question here, is QRev required? It's not, clearly, because I can get a discharge value directly from RSQ. But QRev is required for some agencies. So if it's required for you, now at least you can understand a little bit about why you might see different results in the two different programs. So I've talked a lot about this, but if you want to dive into more post-processing, I encourage you to check out Chapter 7. Xue actually talks about how to export your data to bring it into QRev. She goes over tips and tricks about processing your data in RSQ, so I highly encourage you to check that out. So one last thing I'll say is that I've talked a lot about post-processing in this question here, but there's nothing better than in-field real-time QC. So make sure that you're setting up your measurement correctly. Make sure you're doing a compass calibration, checking for a moving bed. And then we also give you a lot of real-time QC information. We're constantly feeding you information on the GPS, what your communication level is like, what one transect is like compared to another one. So make sure that you have your QC window turned on. In RSQ, you can turn this on with a simple Control Q. In River Surveyor Live, you'll have to right click there and select Show QC Window. Seeing any errors or warnings in the field will allow you to tackle those, and hopefully then you walk away with a good measurement. All right, and I'll pass it over to Chris.
Hey there, Brittany. Thank you so much. You did a great job, all of you. So we know we're over time, but even though we were able to use this time to get into the weeds with these top 6 questions asked by our ADCP users, we have a number of questions that have come in during the live presentation. So we're going to do our best to try and answer as many questions as possible in the next 10 to 15 minutes. But please know that if we don't get to your question, we're going to consolidate all of them. We're going to answer them and send out a document as part of the care package that's going to go out after this webinar. So let's go ahead and just go around the table here. We'll start with Isaac, and Isaac's going to address some of the questions that have come in via chat.
Yes, thank you, Chris. And there's a lot of good questions, but following his excellent description of RSQ and QRev, there's a question about it. Somebody is a little bit confused about what's River Surveyor Live for versus RSQ. And so I'll help clarify that, because Brittany said that you can open River Surveyor Live or M9 files in RSQ. So River Surveyor Live and River Surveyor Stationary Live are the original softwares for the M9 and S5, not to be confused with the RS5. And so that's still the software that you use to make a discharge measurement for an M9 or an S5. RSQ is for making discharge measurements with an RS5, but it has the added feature that you can open files that have been collected using River Surveyor Live, because there are some post-processing capabilities in RSQ that aren't available in River Surveyor Live. So that's the difference there. And with that, I'll pass it over to Xue for a question.
All right, so I'm scanning through here. Do you need to enter a magnetic declination for a stationary measurement? I have not seen a location to enter this information in River Surveyor Stationary Live software. Yeah, so you won't see a magnetic declination for either stationary, for River Surveyor, or for the RS5. And the reason is because we use the azimuth method for stationary. So you do have to either measure or enter that tagline azimuth, and then your velocities will be projected perpendicular to that azimuth tagline. So when you have a magnetic declination, that value is actually added to both that azimuth heading, but also to those vectors. And so because going to be adding that value to both of those things, it actually doesn't make any difference in the discharge calculation. So it's actually not needed in that calculation. Brittany, you want to grab another question?
Yeah, I'm going to quickly answer this question about the first question that I got. Could you please explain why it must be reciprocal transects? So for the moving boat method, I mentioned that you'd need to collect reciprocal transects, and that has to do with averaging out those different directions, and it has to do actually with the fact that your heading is going to be playing an impact on your track. And so you want one direction and then the other direction and average those out. So that's why you always need reciprocal pairs of transects.
Okay, I see another two here that I think we can combine. So we have a question from Chance on any advice on beam separation issues. Sometimes there's no issue and sometimes there is. Does a transducer depth have any impact on beam separation? And so, yeah, it's a very good question. And in my example for transducer depth, between the two different sites, we had a very small site, very smooth flowing water, and then a relatively large site with very fast flowing water and some surface waves. The answer for those two sites is yes, the transducer depth can matter, because if it's very smooth, you can have a pretty shallow transducer depth. If there's some surface turbulence, you want the transducer as far in the water as possible to try and get it below any zone of aeration. So our frequencies don't transmit well through air. Maybe a few small air bubbles, but if you have a lot of air entrainment in the water below the transducer, that's potentially going to cause beam separation issues. And then the other question I wanted to tie this into is what could cause the loss of bottom track samples, because I talked about that. For this site, we missed like one or two bottom track samples across the transect for this video shoot, the Blue River and flood. And so what we think in this case, because it coincided with beam separation, is that these just had some beam separation from some air entrainment as the boat's going across the channel. So that can cause loss of bottom track samples. There are other things too, very difficult, like very high sediment loads and operating near the limit of the ADCP. It might have a hard time tracking the bottom, or if you have very angular substrate, and you're moving quickly, or the combination of the speed and the substrate can cause bottom track issues. So that's why we recommend, if you have GPS, always run your system with the GPS connected and your compass calibrated, so that you have issues with bottom tracking, you do have a second option.
All right. A question, at what point do you use the composite track option? That's a great point that we didn't bring up during the presentation. Composite tracks is a feature that we have. It's available on the Smart page, so you can toggle it on or off. And it's a feature where if you, for example, lose bottom track and you have a GPS or GNSS ship track, you'll be able to fill in those missing bottom track holes with your GPS. And then vice versa. If you lose GPS information, then you can backfill basically with your bottom track information. And that happens automatically on the fly if you do have this feature enabled. It's basically up to you whether you want to use this feature or not. I will say that folks, for example, at the USGS actually prefer to turn off the feature, just because they want to be able to see the raw data come in and determine while they're in the field the quality of that data. So instead of having an automatic filling in of holes and having a good looking measurement, they actually prefer to see in the field, okay, I've got these bottom track holes, I've got these GPS issues, so that they can still be in the field when they actually take care of those issues. But if you're at a site where you know that you basically always have a certain type of issue, and you're after that Q value at the end of the day, you're welcome to turn the feature on, and it does do a good job of covering track reference holes when they exist. Brittany.
All right, take one more question here. So, as I understood, it is possible to choose the track references simultaneously. I guess this will reduce battery and memory storage faster. So I just want to clarify here. So you're going to select a track reference to be viewing as your primary. But if you have GNSS connected, then you'll always be recording all 3 track references if you have the GNS connected and powered on. So at that point, you'd be recording bottom track, GGA, and VTG. And so you're just selecting which one you want to view as your primary for the calculations, and then you'll have access to the other track references in post-processing.
Okay, and so we have another question here. Is this kind of ADCP more related to research in rivers, little transects? Is it possible to operate in little bay or fjords in Antarctica? So that's a good question. Yeah, we are very focused on discharge in rivers and streams and a bit smaller streams because we have RS5 focus. So the RS5 is aimed at smaller channels, shallower channels. The M9 can be used in deeper depths, so velocity profiling to 40 meters and bottom detection to 80 meters. And if you're looking for mapping, the M9 is integrated with HYPACK survey software. And the RS5 will be in 2024. So there are options for these ADCPs to be used for more research-related topics. If it's not just discharge, you can do some mapping of velocity and bathymetry with the two, or with the M9 currently with HYPACK, and then soon with the RS5. So that's a good question. Thank you. With that, pass it to Xue for another.
Okay, I think in the interest of time, this is going to be the very last question that we answer. Let's see. Is the vertical beam depth more sensitive to pitch and roll movements? And bottom track depth will be averaged, and it can give a good depth even when pitch and roll occurs. I think that's a great point that we didn't mention. When you do have pitch and roll and you have that vertical beam, which is, for example, slanted like this, that vertical beam slant distance is going to be larger than your actual depth right under your instrument. So if you are pitching and rolling quite a bit, especially with the M9, you may want to choose bottom track as your depth reference. And I say especially with the M9 because with the RS5, we actually do a pitch and roll correction on the vertical beam and the bottom track depths. So keep that in mind when you're using the RS5. You should see no difference whether your RS5 is pitched up or moving around versus perfectly vertical. So those values will be corrected for you in the RS5.
All right. So let me see here. I'll try and answer one more question here. I guess just really quickly, since a lot of people are asking this, this is being recorded and it will be shared out afterwards. So there's a couple of people asking if that'll be shared out afterwards. So have no fear, we'll be sending it out. All right, let's see. Oh, here's a good one. How often should you send in your ADCP for servicing and accuracy confirmation? So the really great thing about acoustics is that there's no moving parts. So it doesn't require periodic calibration. So as long as your beams look as they should in an SNR plot, then you can assume that your instrument is working well. So there's no reason to send it in unless you think that there is something wrong. We do sell a Castaway CTD. So if you need to correct your sound speed information, and you have one of our Castaway CTDs, that does require annual service. So that would be the only instrument that you'd need to send in for regular service. But all of our ADCPs, as long as they're operating fine, you don't need to send them in.
All right, thank you, Brittany. And then following on that CTD comment, there was a question about we operate in freshwater streams, but and the specific conductance is 300 microsiemens. But what if the salinity range is much higher? And that, so we sell the SonTek Castaway CTD, which can be used to correct for the sound speed and the effects of density, gradients, salinity. And it is only needed when you're working in mixed or saline environments. So if it's freshwater, and within a range, it's not going to make much of a difference. But if you are working, say, in an estuary or in a coastal zone where you have high salinity, you should either be using the option in the software to enter a measured salinity to correct for depths, or you can use the Castaway CTD and do cast and then import and correct your data using the Castaway CTD.
Next question, do you need reciprocal transects with a stationary measurement? The answer is no. The idea is that with a stationary measurement, because you're sitting at each station for usually, I don't know, 20 to 40 seconds is the usual numbers I see. We basically assume that you've covered enough time measuring across that channel to basically go from one bank to another and then stop. So the answer is no, you don't need to go back and forth during a stationary measurement.
All right. So here's a question on compass calibration. Do I have to repeat the compass calibration if the software crashes after the calibration? As long as you completed the compass calibration, no, you do not. The compass calibration gets saved to the instrument, and it will continue to use that calibration going forward until it is replaced.
Okay, so let's see. Okay, there's a question. We had a problem with internal temperature rise, and the beam velocity depends on the temperature. So I'm gonna kind of guess that this is asking if there's a problem with the temperature sensor. Can you still use the measurement? And we do have an option to enter an externally measured temperature if you had another temperature sensor at the site. So that can be applied in post-processing in the software.
All right. Well, thank you everyone for sticking with us through this extended version of our webinar. There are a lot of great questions. We obviously have not been able to get to all of them, but as I mentioned earlier, we'll consolidate all your questions. We will respond in a written document and send that around as part of our care package. In that care package, you're also going to get a copy of this presentation. You're going to get a copy of the recording of this presentation. You're also going to get a very special ADCP Advanced Users Guide, Quick Start Guide that has not been made available to the public yet. And of course, you're going to get links to our video training series. Again, I'm Christina Irossi. From all of us here at SonTek San Diego, we appreciate you participating and watching us today. Thank you.